Section 9.3, Comparison of Procedures for Solving Linear Systems. In computer jargon, an arithmetic operation, plus, minus, times, division, on two real numbers is called a flop, which is an acronym for floating point operation. The total number of flops required to solve a problem, which is called the cost of the solution, provides a convenient way of choosing between various algorithms for solving the problem. So, as an example, how about we talk about Gauss-Jordan elimination? So we have some sort of matrix with, let's say, some values in it, and we want to get zeros underneath the first number, whatever it is. We also want to make that first number into a leading 1, and then do the same thing for the rest of the columns. So in order to get that leading 1 in the first entry, you would need n different multiplications. And then in order to get a 0 underneath it, you would need n multiplications and n additions. So that's 2n. And then there's n minus 1 of these rows underneath. So you could imagine that getting this first column in row echelon form would require n plus 2n times n minus 1 operations, or n plus 2n times n minus 1 flops. So then you could figure out how many flops are required to get the leading 1s and 0s in all of the remaining columns, and it would take, it's not that difficult because it actually follows a pattern. As you can see, you can extrapolate from the first one, but then you have to add up all of these sums, and you have to use formulas for the sum of the first n cubes, etc. So it gets a little bit technical, but it's not so bad. Eventually you get a polynomial in terms of, with the highest degree 3, so the third degree polynomial, and we approximate that polynomial with just the leading term, which is 2/3 n cubed. So that's for the getting the leading ones in. That's the Gauss-Jordan elimination, the forward phase. And then to actually solve for each of the variables, we go back and plug in with the backward phase, and you can do more calculations and see that cost in flops would be approximately n squared. And then there's various other matrix procedures that we could do, different algorithms like LU decomposition, forward substitution to solve Ly equals B, backward substitution to solve Ux equals Y, the A inverse reduction, and computing A inverse B, and the table gives the approximate cost in flops for each of these algorithms. Let's do an example by approximating the time required to execute the forward and backward phases of Gauss-Jordan elimination for a system of 1 million equations in 1 million unknowns using a computer that can execute 10 petaflops per second, where a petaflop is 10 to the 15 flops. So we're starting with n equals 10 to the 6. We know that the petaflops for the forward phase from our table is approximately 2/3 n cubed, but that was in flops, so we have to divide by 10 to the 15th, so I'll multiply by 10 to the minus 15th, and that converts it to petaflops, and that is equal to 2/3 times 10 to the 6, because that's what our n is, cubed, times 10 to the minus 15th, and that's equal to 2/3 times 10 to the 3rd. So that's the petaflops required for the forward phase. Let's see about the backward phase. So the petaflops that we would need for the backward phase, well, that's approximately, again, by our table, n squared, and we divide by 10 to the minus 15 to convert to petaflops, and that equals 10 to the 6 squared times 10 to the minus 15, which is 10 to the minus 3. So that means that now we can figure out how long each phase should take. The time for the forward phase should take about the 2/3 times 10 to the third that we computed before times 10 to the minus 1 seconds, because the computer can execute 10 petaflops per second, so I'm just dividing by 10. So that means it should take the computer 66.67 seconds to do the forward phase. As far as the backward phase goes, just the plugging in, we expect this should be a lot faster. So the time for the backward phase is about 10 to the minus 3 times 10 to the minus 1 seconds. And that's really, really fast. It's 0.0001 seconds.